Welcome to tonight's journey into the hidden ocean. The day has ended across the surface world. It is time to release your waking thoughts. Your mind can find rest in the quiet. We explore the vast mysteries of our planet. Tonight brings us to the remote Indian Ocean. This is a space of absolute natural tranquility. You are safe in your comfortable resting place. Breathe at your own natural and steady rhythm. The outside world fades entirely into the background. Only the steady calm of the narrative remains. We focus entirely on geological wonders this evening. Let your muscles relax deeply into your bed. The journey ahead requires absolutely no physical effort. You can simply listen and slowly drift away. Our destination lies far below the restless waves. Peace exists deep within the marine geological environment. The Indian Ocean covers millions of square kilometers globally. It is the third largest oceanic division on Earth. Water connects the eastern and western hemispheres right here. Our exact focus is a massive submerged mountain chain. Scientists officially call it the Central Indian Ridge. This immense geological feature divides the deep ocean floor. It stretches across a remarkably vast longitudinal marine expanse. The primary coordinate center near 25 degrees south latitude. The eastern coordinate sits precisely at 70 degrees east. This location places the ridge far from any coastline. No continental landmass interrupts this remote marine structural sector. The nearest populated islands remain hundreds of miles away. Vast stretches of unbroken water conceal the rugged topography. Satellite altimetry reveals the hidden geological structures far below. Gravitational anomalies map the underwater peaks and valleys perfectly. Oceanographers rely heavily on these precise orbital satellite measurements. The ocean's surface offers no hint of the mountains. Millions of cubic kilometers of seawater provide perfect cover. The physical isolation here is mathematically and geographically absolute. Our location features a highly complex tectonic plate boundary. It is a classic divergent mid-ocean ridge structural system. The Earth's crust literally pulls apart right at this spot. Three massive tectonic plates meet at one singular central point. Geologists name this specific area the Rodriguez Triple Junction. The African plate drifts slowly toward the western horizon. The Indo-Australian plate moves steadily toward the northeast direction. The Antarctic plate anchors the southern portion of the ocean. This junction represents a rare and fascinating geological intersection. Magma rises from the deep mantle to fill the gaps. The spreading rate is considered intermediate by modern marine scientists. The plates move about 30 to 50 millimeters every year. This slow separation creates highly specific volcanic rock formations. Crustal divergence shapes the entire regional bathymetry of the ocean. Molten rock meets freezing water precisely at the tectonic boundary. Rapid cooling forms fresh pillow basalt formations on the seafloor. Earth creates new solid surface continuously in this active rift. The immense tectonic forces operate in complete and total silence. The sheer mass of the moving lithospheric plates astounds researchers. Continental drift happens continuously in this hidden benthic marine realm. Human knowledge of this oceanic ridge is relatively quite recent. Early sailors crossed the ocean completely unaware of the mountains. The extreme depths hid the peaks from ancient maritime navigators. Modern sonar eventually revealed the jagged underwater physical landscape. Scientist Marie Thorpe mapped these complex features extensively during the 20th century. She worked alongside geologist Bruce Heesen for many dedicated decades. Their detailed cartography helped prove the theory of continental drift. Thorpe identified the central Rift Valley through raw numerical data. She noticed the continuous V-shaped depression using mathematical depth soundings. Her meticulously hand-drawn maps changed marine geology as a discipline. The central Indian Ridge appeared clearly on paper for the first time. Subsequent scientific expeditions confirmed her groundbreaking topographic oceanic theories. Research vessels deployed multi-beam echo sounders for ultimate verification. The acoustic sound waves painted a high-resolution picture of the bottom. Every peak and valley became a precise digital computer model. Modern science transformed a blank void into highly detailed geography. The physical depth of this underwater ridge is truly profound. The highest mountain peaks sit roughly 2,000 meters deep. The central axial Rift Valley plunges much further down into the crust. Some localized trenches reach 4,000 meters below sea level. The average regional depth hovers steadily around 3,000 meters. Surface weather has absolutely no physical impact down in this zone. Violent storms and hurricanes cannot penetrate the dense water column. The thermal structure changes drastically with ongoing vertical descent. The sunlit epipelagic zone gives way to the twilight mesopelagic. We focus entirely on the dark bathyal and abyssal zones. The sheer volume of water creates a massive environmental buffer. Ocean currents move quite differently at these extreme oceanic depths. Antarctic bottom water flows slowly over the rugged ridge terrain. This incredibly dense liquid shapes the local marine benthic climate. The precise measured depth varies significantly along the ridge axis. Geological fault lines create sudden vertical drops in seafloor elevation. A single underwater cliff can fall 500 meters straight down. The topography rivals the largest terrestrial mountain ranges on land. The immense physical scale defies ordinary human visual comprehension. Water temperatures plummet far below the warm sunlit ocean surface. The thermocline acts as a sharp and permanent thermal barrier. Warm surface water stays completely separated from the freezing depths. The ambient temperature at the ridge remains perpetually near freezing. It hovers steadily around 2 degrees Celsius throughout the year. This specific thermal state remains constant across centuries of time. Seasonal climate changes do not affect the deep abyssal plains. The chilling cold perfectly preserves organic matter falling slowly downward. Only active geothermal vents break this freezing ambient temperature pattern. Hydrothermal activity occasionally heats the surrounding ocean water to extremes. Otherwise, the profound chill dominates the entire geological underwater landscape. The extreme cold significantly increases the density of the seawater. This dense polar water carries high levels of dissolved oxygen. The specific chemical composition sustains unique deep marine biological processes. Thermal stability provides a reliable foundation for the deep ecosystem. Hydrostatic pressure defines the absolute physical reality of this environment. The sheer weight of the overlying water column is immense. Every 10 meters of depth adds 1 atmosphere of pressure. At 3,000 meters, the physical pressure is truly crushing. It reaches 300 times normal surface level atmospheric pressure. This equals over 4,000 pounds per square inch continuously. The immense physical force compresses water molecules very slightly together. Gases behave quite differently under such extreme oceanic physical loads. Nitrogen and oxygen dissolve seamlessly into the dense fluid matrix. The calcite compensation depth occurs near these specific pressure metrics. Calcium carbonate begins to dissolve rapidly into the surrounding seawater. Delicate shells and skeletons cannot maintain their solid mineral structure. The immense pressure prevents superheated water from boiling easily underground. Even near hot subterranean magma, the liquid remains highly stable. Human engineering requires thick titanium spheres to survive these forces. The natural environment exists in a state of heavy equilibrium. The constant pressure ensures a perfectly stable physical marine domain. Solar radiation cannot penetrate this massive volume of ocean water. The photic zone ends thousands of meters above the ridge. Photons lose their kinetic energy in the upper pelagic layers. Red visible light disappears within the first few surface meters. Blue light travels furthest before finally fading completely away forever. The central Indian Ridge exists in a state of absolute blackness. This is the permanent defining condition of the aphotic zone. No diurnal solar cycle exists in this deep benthic environment. Day and night have absolutely no biological meaning down here. The darkness is a tangible, physical oceanographic property of water. It allows for the perfect preservation of deep aquatic silence. Bioluminescence occasionally provides tiny flashes of organic chemical light. These brief organic sparks are the only natural illumination available. The dark rocky terrain absorbs any stray light photons instantly. Shadows simply do not exist without a reliable directional light source. The complete visual void creates a profoundly peaceful atmospheric setting. The absolute lack of sensory input invites deep mental relaxation. The terrain surrounding the central ridge is highly structurally complex. Massive transform faults slice cleanly across the entire mountain chain. These deep faults run perpendicular to the main spreading center. The Marie Celeste fracture zone is one prominent geological example. It offsets the main ridge axis by several dozen kilometers. The Argo fracture zone creates another massive geological seafloor scar. These deep marine canyons channel cold oceanic bottom currents efficiently. The vast abyssal plains stretch outward from the flanking mountains. Thick layers of pelagic sediment cover the flat ocean floor. This fine sediment accumulates at incredibly slow natural geological rates. It takes an entire millennium to build 1 single millimeter. The deep mud consists of microscopic siliceous biological ocean remnants. Volcanic ash from ancient terrestrial eruptions also mixes in slowly. The central axial rift valley contains fresh, glassy basalt rocks. Pillow lavas form distinct bulbous shapes directly on the seafloor. Sheet flows create wide, flat, paved areas of solid rock. Steep fault scarps form massive and sheer underwater cliff faces. The local geology is raw, fully exposed, and perfectly preserved. Earth's internal structural architecture is clearly visible along the ridge. The central Indian Ridge remains a monument to planetary forces. It stands as a testament to deep geological time scales. Millions of years of activity shape these silent underwater peaks. The ocean protects this landscape from human disturbance and noise. The sheer scale of the ridge commands a quiet respect. Every square meter holds complex mineral and chemical oceanographic secrets. The story of this underwater mountain range begins in the late 19th century. British scientists launched the HMS Challenger expedition in 1872. This historic voyage marked the birth of modern global oceanography. Researchers used heavy-weighted ropes to measure the deep ocean depth. They recorded unexpected shallow points in the middle of the Indian Ocean. Early soundings showed depths of 2,500 meters. Surrounding abyssal plains reached depths exceeding 5,000 meters. These early measurements provided the first evidence of a submerged highland. Technology remained too primitive to map the entire underwater structure. The true scale of the ridge remained hidden for many decades. Sonar technology advanced significantly during the Second World War. Naval vessels continuously recorded echo soundings across the global oceans. This acoustic data eventually reached the Lamont Geological Observatory. Geologist Marie Thorpe began analyzing these soundings in the 1950s. She plotted thousands of depth measurements on massive paper charts. Her colleague Bruce Heesen initially dismissed her findings as coincidental. Thorpe noticed a distinct V-shaped cleft running along the mountain peaks. This central rift valley indicated active geological separation of the crust. The central Indian Ridge finally appeared on their groundbreaking physiographic map. They published the first comprehensive map of the Indian Ocean floor. The scientific community realized the ridge was part of a global system. A coordinated international effort was required to understand this vast region. The International Indian Ocean Expedition launched in 1959. This massive project involved 40 research ships from 13 different nations. The historic expedition lasted for 6 years of intensive data collection. The American research vessel VIMA collected vital sediment core samples. These cylindrical samples revealed the geological history of the deep seabed. The research ship Atlantis II towed magnetometers behind its steel hull. Instruments recorded alternating bands of magnetic polarity in the oceanic crust. These distinct magnetic stripes proved the theory of continuous seafloor spreading. New oceanic crust was constantly forming at the crest of the ridge. Molten rock erupted from the mantle and cooled in the freezing seawater. The cooling basalt locked in the current magnetic field of Earth. The spreading ridge pushed older crust outward at a very steady rate. Scientists calculated a spreading rate of 3 to 5 centimeters annually. This specific velocity classifies the region as an intermediate spreading ridge. The expedition also mapped the complex fracture zones crossing the mountains. The Marie Celeste fracture zone displaces the ridge axis quite significantly. The Argo fracture zone creates deep trenches perpendicular to the main ridge. Researchers focused their attention on the southern end of the mountain chain. They discovered a unique geological feature called the Rodriguez Triple Junction. This tectonic intersection sits at 25 degrees 30 minutes south. The exact longitude is 70 degrees 0 minutes east. 3 massive tectonic plates meet at this precise geographical point. The massive African plate slowly drifts toward the western horizon. The Indo-Australian plate moves steadily in a northeastern direction. The Antarctic plate pushes southward toward the frozen southern continent. The active triple junction creates a Y-shaped pattern on the ocean floor. The central Indian Ridge forms the northern arm of this massive intersection. The southeast Indian Ridge branches off to the lower right side. The southwest Indian Ridge extends outward toward the lower left side. Mapping this junction provided crucial data for modern plate tectonic models. Exploration eventually shifted toward finding active hydrothermal vents in the region. Scientists knew thermal vents existed in the Pacific and Atlantic Oceans. The Indian Ocean remained completely unexplored for deep hydrothermal activity. The Japanese Agency for Marine Earth Science and Technology initiated a targeted search. They deployed the Advanced Research Vessel Kairai in 1997. The ship Kairai carried highly advanced deep-sea exploration equipment on board. The science team focused on the first segment north of the Triple Junction. They analyzed water columns for chemical anomalies indicating thermal vent plumes. Sensors detected high concentrations of methane and dissolved trace manganese. A specialized deep-tow camera system was carefully lowered to the seafloor. The camera captured blurry images of highly unusual biological communities. The dedicated team returned in August 2000 for a closer look. They brought the remotely operated vehicle Kaiko for detailed visual observation. Kaiko descended safely to a depth of 2,400 meters. The precise coordinates were 25 degrees 19 minutes south. The robotic lights illuminated towering chimneys composed of solid sulfide minerals. Black superheated smoke billowed from the mineral structures into the ocean. This historic moment marked the discovery of the Kairai hydrothermal field. Temperature probes measured the venting fluids at 360 degrees. The surrounding bottom water measured a frigid 2.4 degrees. The extreme heat is generated by shallow magma chambers beneath the crust. The active Kairai field spans an area of roughly 50 by 50 meters. It sits securely on the western wall of the Central Rift Valley. Scientists observed dense swarms of specialized shrimp living near the active vents. This biological discovery fundamentally changed our understanding of deep-sea ecosystems. The Indian Ocean vents hosted complex species distinct from other major oceans. A second major hydrothermal discovery occurred in the year 2001. A multinational team sailed on the United States research vessel Melville. They explored a volcanic region further north along the main ridge axis. They located the Edmund hydrothermal field at 3,300 meters deep. The exact latitude was 23 degrees 52 minutes south. The Edmund field proved significantly larger and more active than the Kairai field. Vent fluids here reached an astonishing 380 degrees Celsius. The fluid chemistry contained exceptionally high levels of dissolved iron and hydrogen. The Melville expedition mapped numerous inactive chimneys scattered across the dark seabed. These dormant geological structures indicated thousands of years of past hydrothermal activity. The discovery of these fields completed a massive global biological puzzle. Marine biologists proposed the Indian Ocean served as an ancient evolutionary corridor. It successfully connected the vent fauna of the Pacific and Atlantic Oceans. The most famous biological discovery happened during a much later scientific expedition. Researchers found the unique scalefoot snail living near the Kairai thermal vents. This fascinating gastropod incorporates solid iron sulfide into its unique dermal scales. No other known living organism uses iron in this specific biological manner. Exploring the central Indian ridge requires overcoming very severe logistical challenges. The isolated region experiences frequent cyclones and extremely rough surface weather. The nearest major supply port is often thousands of kilometers far away. Research vessels must carry enough heavy fuel for month-long isolated oceanic journeys. Reliable satellite communication is absolutely essential for transmitting data back to shore. In 2009, Chinese scientists formally joined the deep exploration effort. The research vessel Dayang Yihao conducted extensive sonar surveys of the ridge. They utilized a highly advanced autonomous underwater vehicle named Qianlong. This robotic submarine operated entirely without a physical tether to the surface ship. It glided smoothly just 50 meters above the extremely rugged volcanic terrain. High-resolution multibeam sonar mapped the local topography with truly unprecedented digital precision. The Chinese research team discovered several new remote areas of hydrothermal activity. They officially named one prominent thermal site the Changqing Hydrothermal Field. Another significant geological location was formally designated as the Dashi Hydrothermal Field. These discoveries proved the ridge was far more active than previously thought. Geologists also intensely study the interaction between the ridge and deep mantle plumes. The massive Réunion hotspot sits several hundred kilometers to the geographic west. This rising mantle plume feeds fresh volcanic material toward the active spreading center. Scientists carefully analyze basalt rock samples dredged from the deep central Rift Valley. Chemical isotope signatures reveal a complex mixing of different mantle rock sources. The deep Earth chemistry provides vital clues about early planetary formation processes. The French research vessel Marion Dufresne conducted extensive deep sediment coring operations. They successfully retrieved massive sediment cores measuring up to 60 meters long. These ancient mud layers contain fossilized microscopic marine organisms called foraminifera. The tiny calcium carbonate shells perfectly record historical ocean temperatures over millennia. Researchers accurately reconstruct past global climate changes from these deep ocean records. The towering ridge acts as a massive physical barrier to deep ocean currents. Freezing Antarctic bottom water flows steadily northward along the muddy ocean floor. The underwater mountains force this dense water to navigate through narrow fracture zones. Oceanographers strategically deploy moored instruments to measure these deep abyssal water currents. Submerged current meters record water velocity and direction over several continuous years. The deep physical oceanography of the region remains highly complex and dynamic. Seismologists continuously monitor the entire ridge for frequent underwater tectonic earthquakes. Specialized hydrophones suspended in the water column detect distant acoustic seismic signals. Magma moving beneath the crust generates distinct low-frequency acoustic rumbles. Massive tectonic plates grinding past each other produce sharp seismic cracking sounds. These acoustic sensor arrays can pinpoint deep earthquake locations with very high accuracy. The ridge experiences thousands of tiny micro-earthquakes every single calendar year. Most of these minor tremors register well below a seismic magnitude of 3. Occasionally, larger seismic events trigger underwater landslides along the steep rift walls. The resulting heavy debris flows drastically alter the local biological benthic habitats. Mineral prospectors have recently shown significant interest in the central Indian Ridge. Seafloor massive sulfide deposits contain highly valuable industrial metals like copper and zinc. The International Seabed Authority strictly regulates exploration contracts in these international waters. Several nations currently hold official permits to assess the mineral resources located here. The central Indian Ridge represents a massive tectonic boundary. It separates the African plate from the Indo-Australian plate. This geological seam stretches across the deep ocean floor. Tremendous forces constantly pull these enormous tectonic landmasses apart. The ridge marks a divergent boundary of planetary scale. Molten rock rises from the mantle to fill the gaps. New oceanic crust forms continuously along this central axis. The southern end meets the famous Rodriguez Triple Junction. Here, three major tectonic plates intersect in the darkness. The Antarctic plate joins the African and Indo-Australian plates. Geologists map this complex junction with acoustic sonar systems. The intersection creates highly fractured zones of crustal weakness. Scientists classify this region as an intermediate spreading ridge system. The tectonic plates move apart at very specific speeds. Geodetic sensors measure an expansion rate of precise increments. The separation averages about 40 mm every single year. This rate varies slightly along the length of the ridge. Northern segments spread closer to 30 mm per year. Southern sections accelerate toward 47 mm each passing year. This speed dictates the physical shape of the mountain range. Fast-spreading ridges usually possess relatively smooth topological profiles. Slow-spreading ridges develop deep and jagged central rift valleys. The central Indian Ridge exhibits features of both extremes. A distinct axial valley runs down the mountain center. This valley measures nearly 15 kilometers across in places. The valley floor drops 500 meters below the peaks. Deep beneath the rift valley lies a liquid magma chamber. This reservoir supplies molten material to the ocean floor. Magma ascends through narrow fissures in the cooling crust. The liquid rock meets freezing seawater at the surface. Rapid cooling creates distinctive geological structures called pillow basalts. These bulbous rock formations resemble large stacked stone cushions. A glassy rind forms instantly on the lava exterior. The interior cools slowly, creating fine-grained crystalline rock structures. Basalt covers most of the upper oceanic crust layer. This dark igneous rock contains high concentrations of iron. Magnesium also makes up a significant portion of the basalt. Sometimes the lava erupts faster, creating flat sheet flows. These flat plains of rock pave the axial valley floor. Sonar mapping reveals extensive fields of recent volcanic eruptions. Beneath the basalt layer rests a different kind of rock. Geologists call this deeper crustal material by the name gabbro. Gabbro forms when magma cools slowly deep underground. The slow cooling process allows larger mineral crystals to grow. Researchers sometimes find gabbro exposed on the seafloor surface. Massive tectonic faults pull the upper crust completely apart. These geological structures are known as oceanic core complexes. Detachment faults bring deep rocks up to the ocean floor. The research vessel Sun mapped several of these unique complexes. Scientists deployed the ROV Keel 6000 to collect rock samples. The robotic arms retrieved pristine pieces of deep crustal gabbro. Laboratory analysis revealed large interlocking crystals of dark minerals. These samples provide direct windows into the lower oceanic crust. Below the gabbro lies the actual boundary of the mantle. The Moharovicic discontinuity separates the crust from the mantle layer. Mantle rock consists primarily of a dense material called peridotite. Peridotite rarely reaches the surface of the Earth intact. The central Indian Ridge exposes peridotite along steep fault scarps. Tectonic stretching literally tears the entire crustal layer open. Deep mantle rocks slide upward along massive corrugated fault planes. peridotite contains abundant amounts of a green mineral named olivine. This mineral gives the pristine rock a pale greenish hue. Pyroxene crystals also exist within the solid peridotite matrix. These minerals formed under extreme pressures deep inside the planet. Exposing them to ocean water triggers profound chemical changes. Seawater seeps down through deep cracks in the exposed mantle. The water reacts chemically with the olivine and pyroxene crystals. This hydration process transforms the hard peridotite into serpentinite. Serpentinite is a much softer rock with a scaly texture. The chemical reaction physically expands the volume of the rock. This expansion causes further fracturing of the surrounding seafloor. Serpentinization also releases significant amounts of natural geothermal heat. The process generates hydrogen gas and alkaline fluid byproducts. Scientists study these reactions to understand early Earth chemistry. The Japanese research vessel Haku Maru investigated these exact sites. Oceanographers measured temperature anomalies above the exposed mantle rocks. They detected the chemical signatures of serpentinization in the water. The geological composition of the ridge includes many specific minerals. Plagioclase feldspar appears frequently in the collected basalt samples. These white crystals form early in the magma cooling process. They often float within the darker liquid rock matrix. Spinel is another mineral found in the deep mantle rocks. It contains trace elements like chromium and aluminum oxides. Scientists analyze spinel to determine the melting temperature of magma. The chemical ratios act as geological thermometers for researchers. Titanium dioxide levels vary across different segments of the ridge. Higher titanium concentrations indicate magma originating from deeper mantle sources. The Marie Celeste fracture zone interrupts the continuous mineral patterns. This massive transform fault shifts the ridge axis sideways. Rock compositions change abruptly across this major tectonic boundary. Volcanic heat drives complex hydrothermal circulation systems through the crust. Superheated water dissolves metals from the surrounding basaltic rocks. The fluid carries iron, copper, and zinc toward the surface. When this hot fluid meets cold sea water, minerals instantly precipitate. Polymetallic sulfides accumulate to form massive towering chimney structures. Chalcopyrite deposits give the chimneys a distinct brassy yellow color. Sphalerite contributes zinc and adds dark gray or black tones. Pyrite, or fool's gold, forms highly reflective cubic mineral crystals. Anhydrite creates white structural frameworks for the growing chimney walls. These sulfide deposits represent concentrated accumulations of valuable heavy metals. Geologists estimate some deposits contain millions of tons of ore. The Kairai hydrothermal field features extensive polymetallic sulfide formations. ROV Kaiko documented these massive mineral deposits in high resolution. The age of the central Indian ridge spans millions of years. Geologists determine crustal age through the study of paleomagnetism. Earth periodically reverses its global magnetic field polarity. Magnetic north becomes magnetic south at irregular temporal intervals. Iron-rich basalt records the prevailing magnetic direction upon cooling. The seafloor acts like a giant geological tape recorder. Symmetrical stripes of alternating magnetic polarity flank the central ridge. Scientists tow magnetometers behind research ships to map these patterns. The Vine-Matthews-Morley hypothesis explains this fundamental tectonic mechanism perfectly. Each magnetic stripe corresponds to a specific geological time period. Researchers refer to these specific time intervals as magnetic crons. Cron 1 represents the current normal magnetic polarity period. This period extends back roughly 780,000 years. Rocks within the central axial valley fall into this category. Moving outward from the axis, the oceanic crust grows older. Cron 5 corresponds to rocks formed about 10 million years ago. These older rocks lie hundreds of kilometers from the center. Sediment slowly buries the older basalt as it moves outward. The central ridge remains largely free of thick sedimentary blankets. This lack of sediment exposes the pristine volcanic rock formations. Geologists successfully mapped anomalies dating back 50 million years. This mapping reconstruction reveals the historical movement of the plates. The Indian subcontinent drifted rapidly northward during the Cretaceous period. The central Indian ridge drove much of this continental migration. Numerous transform faults slice horizontally across the main ridge axis. These geological fractures accommodate the spherical geometry of the Earth. The Vima Trench represents one of these massive fracture zones. It creates a deep linear valley cutting perpendicular to the ridge. The trench floor reaches depths exceeding 5,000 meters. Friction along these faults generates frequent shallow oceanic earthquakes. Seismometers record constant microseismic activity throughout the fracture zones. The rock inside these fault zones becomes heavily crushed and deformed. Geologists refer to this pulverized rock material as fault breccia. Water penetrates deeply into the crust through these shattered pathways. This deep water circulation alters the chemical structure of the rocks. The fracture zones create distinct boundaries between different magmatic segments. The research vessel Thomas Washington conducted extensive early ridge surveys. Scientists utilized heavy steel dredges to collect deep rock samples. A winch lowered the dredge basket down to the seafloor. The ship slowly dragged the heavy basket up the rocky slopes. This method recovered hundreds of kilograms of basalt and gabbro. Modern expeditions rely on precise autonomous underwater vehicles instead. The AUV Abyss maps the seafloor using multi-beam echo sounders. It flies 50 meters above the jagged volcanic rock terrain. The acoustic sensors generate maps with centimeter-level topographic resolution. Researchers identify individual lava flows and tectonic fault lines. Targeted sampling by ROVs replaces the older blind dredging techniques. Scientists select specific mineral formations for precise robotic extraction. Laboratory technicians slice the recovered rocks into microscopic thin sections. Polarized light reveals the internal crystalline structure of the minerals. Mass spectrometers measure specific isotopic ratios within the rock samples. Strontium and neodymium isotopes provide clues about the mantle source. The central Indian ridge shows a highly unique isotopic signature. It differs significantly from the mid-Atlantic ridge rock chemistry. Scientists attribute this to the ancient Kerguelen mantle plume interaction. Millions of years ago, a massive hotspot altered the upper mantle. This deep thermal anomaly injected distinct chemical elements into the rock. The ridge still erupts magma carrying this ancient chemical fingerprint. Helium isotope measurements in the water column confirm this connection. Helium-3 indicates the presence of primordial mantle gases escaping upward. The geological formation directly supports a hidden deep microbial biosphere. Microbes colonize the microscopic pores within the cooling basaltic rock. They extract metabolic energy directly from the iron-rich minerals. The Kyray hydrothermal field sits at 25 degrees south. It rests at a depth of 2,400 meters. Massive sulfide chimneys rise from the basaltic ocean floor. These towering structures are scientifically classified as black smokers. Superheated fluids billow continuously from their hollow mineral summits. Temperatures here frequently reach 365 degrees Celsius. The surrounding seawater remains at a frigid 2 degrees. This extreme thermal gradient drives the chimney formation process. Dissolved metals precipitate instantly upon contacting the cold ocean. Iron and sulfur combine to form fine dark particulates. These suspended particles create the illusion of thick smoke. The ROV Jason measured these emissions during a 2001 expedition. Scientists observed fluid velocities exceeding 1 meter per second. The immense pressure prevents the superheated water from boiling. A new chimney begins as a fragile anhydrite ring. Calcium and sulfate ions bond rapidly in the mixing zone. This initial white mineral tube grows several centimeters daily. Hotter fluids soon begin flowing through this porous conduit. Copper and iron sulfides deposit along the inner walls. Chalcopyrite forms a dense golden lining inside the throat. The exterior walls thicken with layers of porous sphalerite. Zinc concentrations increase toward the cooler outer mineral margins. Over decades, these structures reach heights of 30 meters. The monolith chimney in the Kyray field stands tall. Researchers mapped its base at roughly 15 meters across. Its sheer mass requires a stable foundation of basalt. Seismic tremors frequently fracture these towering mineral deposits. Fallen chimney fragments create expansive mounds of sulfide rubble. New spires quickly sprout from these broken structural remains. The Edmond hydrothermal field lies further north along the ridge. Its coordinates are 23 degrees and 52 minutes south. The seafloor here drops to 3,300 meters deep. This area features a different class of hydrothermal vents. White smokers dominate specific zones within the Edmond field. These vents emit fluids at slightly lower temperature ranges. Thermometers record values between 200 and 300 degrees. The escaping fluid lacks the heavy dark iron sulfides. Instead, it carries high concentrations of barium and calcium. Silica also precipitates heavily in these cooler vent emissions. The resulting smoke appears as a dense white plume. Barite and anhydrite crystals form the pale chimney walls. These white structures tend to be smaller and more fragile. Japanese researchers documented them using the Shinkai 6500 submersible. A major expedition yielded crucial data on mineral compositions. Seawater percolates through deep faults in the oceanic crust. It travels several kilometers down toward the magma chamber. Intense heat alters the fundamental chemistry of the water. Magnesium and sulfates are completely stripped from the fluid. The modified water becomes highly acidic and chemically corrosive. It leaches heavy metals directly from the surrounding rocks. Buoyancy forces this mineral-rich solution back toward the surface. The upward journey occurs through narrow crustal fracture zones. Hydrogen sulfide gas dissolves heavily into the ascending fluid. This dissolved gas plays a crucial role in vent ecology. Helium isotope ratios indicate a deep mantle origin source. Geochemist Dr. Jean Bougault analyzed these specific isotope signatures. His team linked the emissions to deep magmatic degassing. The central Indian ridge displays unique chemical signature variations. Fluid salinity here differs from vents in the Pacific. Vent architecture varies greatly across the central Indian ridge. Some structures form wide flanges resembling inverted stone pools. Hot fluid pools beneath these horizontal mineral ledges. The trapped water eventually spills upward over the rim. This creates a shimmering mirror effect in the submersible lights. Other chimneys grow as slender spires resembling Gothic cathedrals. Multiple small conduits often merge into a single massive trunk. The Kali chimney complex features dozens of interconnected spires. Active venting shifts constantly between these various mineral nozzles. Mineral deposits seal older fluid pathways over several months. Internal pressure forces the hot fluid to find new exits. This dynamic process creates highly irregular and branching shapes. The structural integrity depends heavily on the mineral composition. Silica-rich chimneys exhibit greater resistance to physical collapse. Sulfide-dominated spires tend to crumble under their own weight. Scientists first detected thermal anomalies here in the late 90s. The research vessel NOR conducted extensive water column surveys. Towed sensors identified distinct chemical plumes above the ridge. Manganese concentration spiked sharply in the collected water samples. Optical backscatter instruments measured increased particle density at depth. These signals guided researchers to the exact vent locations. The autonomous underwater vehicle ABE mapped the Edmund Field. It flew 50 meters above the rugged volcanic terrain. High-resolution sonar revealed clusters of tall chimney structures. Magnetic sensors detected alterations in the underlying basaltic crust. Hydrothermal fluids destroy magnetic minerals within the host rock. This creates a distinct non-magnetic signature around active vents. Dr. Cindy Lee Vandover led biological surveys here. Her team utilized the remotely operated vehicle Jason 2. Titanium sampling bottles collected pristine hydrothermal fluid specimens. A cross-section of a black smoker reveals complex zoning. The central channel remains clear of solid mineral obstructions. Fluid flows through this passage at extreme high velocities. The innermost wall consists of pure crystalline copper iron sulfide. This layer measures only a few millimeters in thickness. Temperatures drop sharply across the chimney wall profile. A steep thermal gradient exists within a narrow space. The temperature falls 300 degrees across 5 centimeters. This rapid cooling dictates the sequence of mineral precipitation. Iron sulfide forms the next distinct concentric mineral band. Zinc sulfide dominates the cooler outer layers of the structure. Amorphous silica fills the microscopic pores between the crystals. This silica cement strengthens the overall chimney architecture significantly. Oxidation occurs on the outermost surface exposed to seawater. Orange and brown iron oxides coat the older mineral formations. Hydrothermal fields on the central Indian ridge evolve continuously. A typical vent site remains active for several thousand years. Tectonic movements eventually shift the underlying crustal fracture networks. The supply of superheated fluid is suddenly cut off. Active black smokers transform into cold, dormant mineral spires. The surrounding seawater slowly degrades the sulfide chimney structures. Oxygen reacts with the metallic sulfides over many centuries. The towering spires eventually collapse into massive rubble mounds. These inactive sulfide deposits contain significant economic mineral value. Geologists study these mounds to understand ancient ore formations. The oceanic crust slowly carries these deposits away from the ridge. Sediment gradually buries the remnants of the extinct hydrothermal fields. New vent systems constantly emerge closer to the spreading axis. This continuous cycle redistributes massive amounts of chemical elements. It profoundly influences the global chemistry of the world's oceans. Researchers deploy deep-tow camera systems to map these vast areas. A sled carrying high-definition cameras glides above the seafloor. Powerful strobe lights pierce the absolute darkness of the abyss. Thousands of overlapping photographs create a comprehensive visual mosaic. These maps reveal the precise spatial distribution of the chimneys. Active vents cluster tightly along specific geological fault lines. The Kairai field spans an area of roughly 2 hectares. It contains over 20 distinct active black smoker chimneys. The largest structures align parallel to the main ridge axis. This alignment indicates strong structural control by tectonic forces. Sonar mapping reveals the underlying topography of the Rift Valley. The vents sit on a raised terrace of pillow basalts. Steep fault scarps bound the hydrothermal field on both sides. These vertical cliffs expose older layers of oceanic crust. Geologists use these exposures to study the regional volcanic history. Measuring these extreme environments requires highly specialized scientific equipment. Standard thermometers would melt instantly in the black smoker fluids. Researchers utilize robust titanium-encased thermocouple probes for accurate readings. The Alvin submersible uses a mechanical arm to insert these probes. The pilot carefully maneuvers the titanium tip into the vent orifice. Real-time data transmits directly to the scientists inside the sphere. Acoustic Doppler current profilers measure the fluid exit velocities. These instruments bounce sound waves off the rising mineral particles. The frequency shift indicates the precise speed of the fluid. Some vents discharge fluid at speeds exceeding 2 meters per second. This incredible velocity prevents the chimneys from becoming clogged. Mass spectrometers analyze the chemical composition of the fluids on board. They detect trace elements down to parts per trillion. This precision allows scientists to trace the origins of the water. Every hydrothermal field possesses a distinct and unique chemical fingerprint. The immense hydrostatic pressure fundamentally alters the fluid dynamics. At 3,000 meters, pressure exceeds 300 atmospheres. This forces the boiling point of water to rise dramatically. Fresh water boils at 100 degrees at sea level. Here, seawater remains liquid even at 400 degrees. This superheated state is known as a supercritical fluid. Supercritical fluids possess properties of both liquids and gases. They can dissolve minerals with incredible efficiency and speed. This unique property allows the transport of massive metal volumes. The pressure also compresses the rising hydrothermal plume. The plume maintains a tight, focused column as it ascends. It rises hundreds of meters before finally losing its buoyancy. Ocean currents eventually disperse the diluted chemical plume horizontally. These deep ocean currents carry the minerals across vast distances. Trace metals from these vents enrich the entire Indian Ocean. The physical forms of these vents are remarkably intricate. Some chimneys display thin, needle-like projections near their summits. These fragile needles grow outward into the cold surrounding water. They break easily when disturbed by passing deep-sea currents. Other structures develop thick, bulbous growths resembling massive stone mushrooms. These bulbous forms indicate a slower, more steady fluid flow. The exterior surfaces are incredibly rough and highly porous. Deep crevices provide sheltered microhabitats for specialized vent organisms. The central Indian Ridge operates as a massive submarine chemical reactor. Tectonic forces expose deep mantle rocks directly to cold seawater. This violent interaction creates a highly complex fluid environment. The Kairai hydrothermal field sits exactly at 25 degrees south latitude. Submarine chemical processes here differ significantly from other global oceanic ridges. Vent fluids emerge at temperatures frequently exceeding 360 degrees Celsius. The pH level at the Kairai field drops to an astonishing 3.2. This extreme acidity closely resembles highly corrosive industrial battery acid. Normal deep ocean water maintains a slightly alkaline pH balance. Background seawater typically measures around 8.1 on the standard pH scale. This stark pH contrast drives aggressive and continuous mineral dissolution. Superheated acidic fluids strip heavy metals from the surrounding basaltic crust. Iron, copper, and zinc dissolve rapidly into the pressurized heated water. The Edmond hydrothermal field lies slightly further north at 23 degrees. Edmond vent fluids display a distinctively different chemical signature. The pH at the Edmond field measures slightly higher, closer to 3.5. This slight chemical variation indicates entirely different subsurface rock interactions. Salinity within these hydrothermal vent fluids fluctuates wildly and unpredictably. Standard global seawater contains about 35 parts per thousand of dissolved salt. Deep oceanic ridge fluids experience a volatile process called phase separation. Extreme geothermal heat and immense pressure cause the fluid to physically unmix. The seawater reaches its critical thermodynamic point deep within the oceanic crust. This extreme state separates the liquid into distinct vapor and brine phases. The newly formed vapor phase rises quickly due to its extremely low density. Vapor-rich fluids exhibit much lower salinity compared to normal background seawater. Conversely, the heavy, dense brine phase sinks deeper into microscopic crustal cracks. Subterranean brine pools can easily exceed 50 parts per thousand in salinity. The Japanese Shinkai 6500 submersible sampled these varied fluids in the year 2000. Marine scientists measured precise salinity gradients near the towering black smoker chimneys. Hydrogen sulfide represents another critically important chemical component in this region. Concentration levels reach an incredible 15 millimoles per kilogram at the Kairai field. This highly toxic, dissolved gas smells strongly of rotting eggs at the surface. However, it serves as the absolute primary energy source for the underwater ecosystem. Chemosynthetic bacteria rapidly oxidize this abundant hydrogen sulfide to generate cellular energy. They efficiently convert inorganic dissolved carbon into biologically usable organic matter. The Edmond vent field shows even higher dissolved hydrogen sulfide concentrations. Geochemical researchers recorded sulfide levels peaking at nearly 18 millimoles per liter. Marine biologists frequently compare this to the famous East Pacific rise vent systems. East Pacific vents often show only half of this measured sulfide concentration. The central Indian ridge clearly sustains a much richer, more potent sulfide environment. Methane gas production adds another fascinating layer of deep-sea chemical complexity. The Earth's upper mantle contains an iron-rich rock known as peridotite. Tectonic faulting exposes this deep peridotite directly to circulating cold seawater. The hydration of the mineral olivine triggers a very specific chemical chain reaction. Geologists universally refer to this transformative mineral process as serpentinization. Serpentinization naturally releases massive quantities of highly combustible abiotic methane gas. Methane concentrations at the Kyre vents routinely exceed 20 millimoles per liter. This immense volume easily rivals the famous Lost City hydrothermal vent field. The Lost City field sits thousands of miles away on the mid-Atlantic ridge. Lost City produces methane through highly alkaline, relatively low-temperature chemical reactions. The central Indian ridge produces methane in highly acidic, extremely high-temperature conditions. This strange hybrid chemical profile fascinates marine geochemists all around the globe. The Japanese research vessel Haku Maru surveyed this exact region in 1993. Scientists aboard detected early chemical anomalies suspended high in the water column. They mapped extensive, invisible methane plumes drifting slowly above the main ridge axis. Microbiologist Ken Takai analyzed these specific hydrothermal fluid samples several years later. He discovered ancient hyperthermophilic archaea thriving beautifully within the toxic chemical soup. These resilient microorganisms consume both dissolved hydrogen gas and abundant methane. Hydrogen gas concentrations in this specific region are unusually and notably elevated. Fluid samples show hydrogen levels hovering around 5 millimoles per kilogram. Typical basalt-hosted hydrothermal vents produce very little dissolved hydrogen gas. The surprisingly abundant hydrogen points directly to deep ultramafic rock chemical influence. Dr. Cindy Van Dover carefully mapped the Edmund Field's complex chemical boundaries. Her research team utilized the remotely operated vehicle Jason in the year 2001. Jason-sensitive titanium probes measured precise oxidation reduction potentials near the active vents. The measured redox potential drops sharply near the boiling vent orifices. This dramatic drop indicates a highly reducing, completely oxygen-deprived fluid environment. Such reducing conditions perfectly preserve fragile organic molecules from immediate destruction. Amino acids can form spontaneously under these exact high-pressure chemical conditions. Dissolved iron concentrations present another striking and significant regional chemical anomaly. The Kyre vent fluids contain up to 24 millimoles of dissolved iron. This iron precipitates almost instantly upon meeting cold, highly oxygenated deep seawater. The violent reaction forms massive, billowing clouds of black polymetallic sulfide particles. Manganese also dissolves quite readily in these superheated, highly acidic subterranean fluids. Manganese levels typically hover around 4 millimoles per kilogram of vent fluid. Unlike reactive iron, dissolved manganese oxidizes very slowly in the deep ocean. It forms a massive, widespread chemical halo surrounding the active vent fields. Oceanographers frequently use this distinct manganese signature to locate hidden hydrothermal vents. Dissolved silica serves as an incredibly reliable natural geothermometer for marine scientists. Silica concentrations easily reach 22 millimoles within the active Edmund hydrothermal field. This specific silica concentration suggests a deep reaction zone depth of several kilometers. The superheated fluids likely originate 3 kilometers beneath the solid seafloor. Carbon dioxide represents the absolute most abundant dissolved gas found here. Continuous magmatic degassing pumps massive volumes of carbon dioxide into the hydrothermal system. The Chi-ray field constantly emits enormous quantities of this invisible greenhouse gas. However, the surrounding deep ocean absorbs it long before it reaches the surface. Helium-3 isotopes provide a direct and undeniable chemical link to the Earth's mantle. Helium-3 is a rare primordial isotope trapped deep underground since Earth's initial formation. The central Indian Ridge vents constantly release unusually high ratios of helium-3. This specific ratio confirms the fluids interact with deep, unweathered magmatic sources. Trace elements like lithium and boron also heavily enrich these rising hydrothermal fluids. Lithium concentrations measure roughly 1.5 millimoles per kilogram of sampled vent water. Boron levels remain surprisingly close to standard background deep seawater values. This unusual boron stability indicates a very short fluid residence time underground. The superheated water travels incredibly rapidly through the deep crustal fracture networks. Rare earth elements display a highly distinctive europium chemical anomaly here. Europium dissolves much more efficiently than other rare earth metals under extreme heat. Hydrothermal plumes floating above the Chi-ray field show incredibly strong europium enrichment. The Pelagia vent field sits further north at exactly 20 degrees south latitude. Pelagia offers a completely different and much calmer chemical environment for study. Venting fluid temperatures here barely exceed a mild 10 degrees Celsius. It represents a low-temperature, highly diffuse submarine chemical venting system. The pH at the Pelagia field remains nearly neutral at approximately 7.5. Dissolved oxygen is still heavily present in these much cooler venting fluids. Hydrogen sulfide concentrations drop drastically below 1 millimole per liter of water. Iron and manganese levels are virtually undetectable at the quiet Pelagia site. This stark chemical contrast beautifully highlights the ridge's vast geological diversity. High-temperature vents like Chi-ray are violently driven by shallow underlying magma chambers. Diffuse vents like Pelagia result from much slower, shallow crustal cooling processes. The turbulent mixing zone creates incredibly steep and dangerous chemical gradients. Fluid temperatures drop from 360 to 2 degrees within mere centimeters of space. The local pH jumps from 3.2 to 8.1 almost instantly upon mixing. These extremely sharp gradients force the rapid and chaotic precipitation of minerals. The mineral anhydrite forms first as the surrounding seawater rapidly heats up. Chalcopyrite crystallizes next as the superheated vent fluid begins to cool slightly. Sphalerite and pyrite follow closely in a very precise, predictable chemical sequence. This sequential mineral precipitation slowly builds the towering, fragile hydrothermal chimneys. The exact chemical composition dictates the chimney's overall structural strength and integrity. Zinc-rich mineral chimneys tend to grow much faster but crumble more easily. Copper-rich chimneys form incredibly solid, enduring mineral structures on the ocean floor. The Edmond field features mostly fragile, zinc-dominated polymetallic sulfide structures. The Chi-ray field routinely produces massive, incredibly dense copper-iron sulfide mounds. Advanced chemical sensors on ROVs continuously monitor these minute environmental changes. Onboard mass spectrometers carefully analyze the captured fluid samples in real time. Scientists map the invisible chemical halos using sophisticated autonomous underwater vehicles. The AUV Abyss surveyed this particular ridge extensively in the year 2007. It detected incredibly minute changes in deep water column turbidity and chemistry. Turbidity strongly indicates suspended particulate matter resulting from ongoing chemical reactions. The overall chemical signature of the central Indian Ridge remains entirely unique. It perfectly bridges the geochemical gap between fast and slow-spreading oceanic ridges. Fast-spreading ridges like the East Pacific Rise display highly uniform fluid chemistry. Slow-spreading ridges like the Mid-Atlantic show extreme and unpredictable chemical variability. The intermediate tectonic spreading rate here creates a perfectly balanced hybrid chemical zone. Deep subsurface faulting allows extensive cold seawater penetration into the hot crust. This deep oceanic circulation maximizes the vital chemical exchange with the mantle. The resulting superheated fluids carry a truly massive dissolved mineral payload upwards. Chemical reactions here also naturally produce highly complex, essential organic molecules. The Chi-ray hydrothermal field supports a dense biological oasis. It sits at 25 degrees 19 minutes south. The depth measures exactly 2,460 meters. Life here depends entirely on continuous chemical energy. Sunlight never reaches this deeply isolated benthic ecosystem. Thick microbial mats cover the surrounding basaltic seafloor. These bacterial colonies form the base of the food web. Japanese researchers mapped these mats in the year 2000. The ROV Kaiko recorded their extensive geographical distribution. White and yellow patches indicate different bacterial strains. Veggiatoa bacteria dominate the cooler peripheral zones of the field. They thrive in water measuring 4 to 10 degrees Celsius. Epsilon proteobacteria form dense filaments near the active vents. These filaments sway gently in the rising thermal currents. The microbial biomass is remarkably high in this region. Scientists measured up to 50 grams per square meter. These bacteria oxidize hydrogen sulfide from the vent fluid. They convert inorganic compounds into usable organic carbon. This process supports thousands of complex living organisms. Swarms of shrimp dominate the immediate vent chimneys. The species Rimicaris Chi-ray is endemic to this ridge. They gather tightly around the active black smoker chimneys. The water temperature here reaches 20 degrees Celsius. These shrimp lack image-forming eyes entirely in adulthood. They possess a specialized dorsal light-sensing organ instead. This organ detects faint thermal radiation from the vents. It prevents them from swimming into boiling water. Population densities are staggering within these active swarms. Researchers counted over 2,000 individuals per square meter. Their combined biomass exceeds 3 kilograms per square meter. The shrimp cultivate bacteria inside their enlarged gill chambers. They graze on these internal bacterial gardens constantly. Dr. Cindy Van Dover studied these unique feeding mechanisms. She noted their constant and rhythmic swimming patterns. The shrimp maintain a delicate position in the mixing zone. They need both oxygenated seawater and sulfide-rich vent fluid. This delicate balance dictates their precise physical location. Moving slightly outward reveals another highly dominant species. Dense beds of Alviniconcha snails cover the rocky slopes. These large gastropods possess round and dark brown shells. Their shells are covered in thick hair-like protein structures. The periostracum layer provides protection from the acidic water. The ambient pH here drops below 4.5. These snails harbor vital symbiotic bacteria in their gills. They rely entirely on these internal microbes for nutrition. Population densities reach 500 individuals per square meter. They form thick and overlapping clusters in the crevices. The water temperature around them averages 12 degrees Celsius. Their total biomass is incredibly high in these patches. It frequently exceeds 10 kilograms per square meter. This makes them a primary component of the ecosystem. The Shinkai 6500 sampled them extensively. Marine biologist Dr. John Copley analyzed their genetic structure. He found them distinctly different from known Pacific populations. Their evolutionary divergence occurred millions of years ago. The most famous resident is the scalefoot snail. Its scientific name is known as Chrysomalon squamiferarum. This fascinating creature exists nowhere else on planet Earth. It was first discovered at the Kyre vent field. The year of this remarkable discovery was 2001. This snail possesses a truly unique biological armor system. Its muscular foot is covered in hundreds of metallic scales. These hardened sclerites are composed entirely of iron sulfides. Greigite and pyrite make up the complex metallic composition. No other known animal uses iron sulfide in its skeleton. The shell itself features 3 highly distinct protective layers. The rigid outer layer contains embedded iron sulfide nanoparticles. The middle layer is a thick and squishy organic periostracum. The smooth inner layer consists of highly calcified aragonite. This composite structure provides exceptional mechanical defense mechanisms. It protects against predatory crabs and highly acidic waters. The internal tissues also house essential symbiotic bacteria. The snail possesses an unusually massive circulatory heart. It comprises 4% of its total body volume. This large heart pumps oxygen directly to its bacterial symbionts. Scalefoot snails live in very restricted environmental zones. They prefer the base of active black smoker chimneys. The fluid flow here remains diffuse and incredibly steady. Temperatures range strictly from 5 to 15 degrees Celsius. Their population density is relatively low compared to shrimp. Scientists count about 50 adult individuals per square meter. Their distribution is highly localized within the hydrothermal field. They only inhabit very specific and stable microhabitats. They require precise concentrations of dissolved iron and sulfides. The Edmund vent field also hosts a small isolated population. It is located at 23 degrees 52 minutes south. The distance between Kyre and Edmund is 160 kilometers. Yet the scalefoot snails at Edmund look remarkably different. Their shells completely lack the dark iron sulfide coating. They appear pale and white instead of metallic black. The genetic structure remains identical across both separated fields. The visual difference stems entirely from local vent fluid chemistry. Edmund fluids contain much lower concentrations of dissolved iron. This prevents the formation of the metallic greigite scales. Other specialized crustaceans inhabit the central Indian Ridge ecosystem. A unique species of yeti crab lives among the rocks. They belong to the recently discovered genus named Kiwa. These crabs have dense setae on their ventral surfaces. These hair-like bristles cultivate thick colonies of symbiotic bacteria. The crabs harvest this bacterial crop using specialized mouthparts. They wave their arms slowly in the warm vent fluid. This rhythmic motion ensures optimal nutrient flow for the bacteria. Population densities of yeti crabs are carefully monitored by scientists. Researchers record about 15 adult crabs per square meter. Squat lobsters from the genus Munidopsis also patrol the area. They act as opportunistic scavengers in this deep ecosystem. They feed on dead shrimp and detached bacterial mats. These lobsters prefer the cooler peripheral zones of the field. They avoid the toxic hydrogen sulfide near the active chimneys. Pythogorid crabs act as the primary apex predators here. They actively hunt the grazing shrimp and smaller juvenile snails. Their powerful claws are adapted for crushing thick calcified shells. Sessile organisms attach securely to the older inactive chimneys. Deep-sea anemones form pale pink gardens on the basalt. They belong to the diverse family known as Actinostolidae. These anemones position themselves in gentle and steady currents. They capture organic detritus drifting from the active vent sites. Their tentacles remain fully extended in the freezing cold water. The temperature here is a steady 2 degrees Celsius. Population densities reach up to 30 individuals per square meter. Stalked barnacles also colonize the exposed rocky basaltic surfaces. They filter feed constantly on suspended bacterial particles. Neolepis barnacles are especially common at the Edmund Field. They form dense crusts on the cooling sulfide mounds. Polychaete worms construct fragile protective tubes in the nearby crevices. The albanellid worms tolerate incredibly extreme temperature gradients. Their tubes touch water reaching 40 degrees Celsius. Their gills extend outward into cooler oxygenated seawater. This biological zoning is incredibly precise and highly structured. Each species occupies a very specific narrow thermal niche. Mobile predators navigate smoothly through the dense invertebrate communities. Zooarcid fish slowly swim among the active shrimp swarms. These eelpouts are typically pale and appear quite lethargic. They measure about 20 centimeters in total body length. They prey silently on weakened or dying adult shrimp. Their cellular metabolism is adapted to the extreme ocean pressure. The pressure here equals 250 standard atmospheres. Eelpouts maintain naturally low population densities across the field. Scientists observe perhaps 1 fish per 10 square meters. Snailfish from the family Liparidae also visit the hydrothermal vents. They possess gelatinous bodies and unusually large pectoral fins. They glide effortlessly through the turbulent thermal water columns. Deep-sea octopuses occasionally approach the extreme vent periphery. The Vulcan octopus searches for hiding crabs among the basalt boulders. These specialized cephalopods lack defensive ink sacs entirely. Ink is completely useless in the permanent oceanic darkness. They rely on sensitive tactile senses to locate their prey. Their long arms probe deep into narrow rock crevices. The central Indian Ridge represents a unique biogeographical province. It serves as a biological crossroads in the deep ocean. It connects the isolated Atlantic and Pacific vent faunas. Yet it maintains a distinctly unique endemic biological population. Approximately 60% of species here are entirely endemic. They are found nowhere else on the entire planet. The evolutionary history of these communities is incredibly complex. Dr. Alex Rogers analyzed the genetic divergence rates extensively. The ridge separated from other systems millions of years ago. This long isolation allowed unique evolutionary paths to unfold. The metallic scalyfoot snail is the prime example of this. The complete lack of tube worms is another defining characteristic. Pacific vents are heavily dominated by giant riftsha tube worms. Atlantic vents are dominated by massive swarming shrimp populations. The central Indian Ridge blends these characteristics quite uniquely. It has shrimp swarms but completely lacks the giant tube worms. It features incredibly dense snail beds instead of worm fields. The total biological biomass at Kairai is astonishingly high. It easily rivals the most productive tropical terrestrial rainforests. The concentration of life is tightly constrained geographically. The entire biological community spans just a few football fields. Beyond this narrow radius, the seafloor is completely barren. The background deep-sea biomass is practically zero by comparison. The vent ecosystem is an isolated island of intense productivity. Carbon fixation rates are carefully measured by automated benthic landers. Chemosynthetic production exceeds 1 kilogram of carbon per day. This massive production occurs within a single square meter. The rapid turnover of organic matter sustains the high biomass. Dead organisms are quickly consumed by the local scavengers. The central Indian Ridge hosts a highly distinct biological ecosystem. This habitat operates entirely without solar energy input. Chemical synthesis forms the absolute base of this local food web. Superheated fluids provide dissolved minerals to specialized microorganisms. These microbes oxidize hydrogen sulfide to produce organic carbon. This process mirrors photosynthesis but relies on geothermal power. The Kairai vent field sits at 25 degrees south latitude. ROV Kaiko first documented this specific biological community in 2000. Japanese researchers measured fluid temperatures reaching 360 degrees Celsius here. A steep thermal gradient exists near the active chimney structures. Water temperatures drop to 2 degrees within just a few meters. This sharp boundary dictates the spatial distribution of animal life. Different species occupy precise thermal niches along the mineral chimneys. The primary consumers gather closest to the venting fluid sources. Swarms of Rimicaris Kairai shrimp dominate the hottest habitable zones. These blind shrimp cultivate bacterial gardens inside their enlarged gills. The shrimp harvest these microbes as their primary food source. Biologist John Copley studied their feeding behavior extensively. He noted their constant movement to bathe their gills in sulfides. Their population density often exceeds 2,000 individuals per square meter. This shrimp species is endemic to the Indian Ocean ridges. They share anatomical similarities with mid-Atlantic ridge shrimp populations. However, genetic analysis reveals a distinct evolutionary divergence. The central Indian Ridge acts as a crucial biogeographical crossroads. It bridges the biological gap between Atlantic and Pacific Oceans. East Pacific rise vents feature massive riftsha tube worm colonies. The central Indian Ridge completely lacks these giant tube worms. Instead, unique gastropods fill similar ecological niches here. The scalyfoot snail represents the most remarkable endemic species. Chrysomalan squamiferae inhabits the base of the black smoker chimneys. This snail incorporates iron sulfides into its dermal scales. It is the only known animal to utilize iron biomineralization. Greigite and pyrite compounds form its rigid external armor. The snail houses symbiotic bacteria within a specialized esophageal gland. This internal gland is extremely enlarged to accommodate the microbes. The host circulatory system delivers hydrogen sulfide directly to them. A massive heart pumps hemolymph efficiently through the snail. The heart accounts for 4% of its total body volume. This biological adaptation maximizes the internal chemosynthetic energy yield. Another dominant gastropod is the Alviniconcha marasyndica snail. These spherical snails cluster tightly in warm fluid diffusion zones. Their shells often appear degraded by the acidic vent water. They rely entirely on Campylobacteria endosymbionts for their nutrition. Secondary consumers prey upon these abundant primary producers. The Ostinogria rodriguezensis crab patrols the periphery of the vents. This bythogoride crab scavenges dead shrimp and smaller gastropods. It also grazes directly on free-living bacterial mats. These bacterial mats coat the basaltic rocks near the chimneys. Filamentous bacteria form thick white patches across the seafloor. Vegeotoa species oxidize hydrogen sulfide at the sediment interface. They thrive where oxygenated seawater mixes with the vent fluids. The Edmund vent field presents a slightly different chemical environment. It is located at 23 degrees 52 minutes south. The water depth at the Edmund field reaches 3,300 meters. RV nor explored this specific site during a 2001 expedition. Dr. Cindy Lee Vandover led the biological sampling operations. The Edmund fluids contain higher concentrations of dissolved hydrogen gas. This altered chemistry shifts the balance of microbial populations. Hydrogen oxidizing bacteria gain a competitive advantage in this location. The macrofauna community structure shifts in response to this change. Anemones attach themselves to the inactive sulfide structures here. Marianactis anemones filter suspended particulate matter from the water column. They capture small crustaceans swept up in the thermal plumes. Apex predators sit at the top of this localized food web. Thermasis pelagicus is a species of endemic zoacid fish. These pink eelpouts navigate steadily through the dense shrimp swarms. They strike rapidly to consume individual shrimp whole. Deep-sea octopuses occasionally visit the vent fields to hunt. Volcanoctopus hydrothermalus uses tactile sensors to locate hidden prey. The entire ecosystem functions with remarkable energy transfer efficiency. Chemosynthetic carbon fixation occurs at incredibly high rates here. The biomass per square meter rivals tropical rainforest ecosystems. Yet this vibrant community exists in total geographic isolation. The surrounding abyssal plain is a biological desert by comparison. Typical deep ocean environments rely on marine snow from the surface. That sinking detritus provides very limited nutritional value. Vent communities generate their own organic material internally. This makes them independent of surface photosynthetic processes. The central Indian Ridge ecosystem is highly dynamic and unstable. Tectonic shifts frequently disrupt the subsea floor plumbing systems. A vent chimney can cease fluid production without warning. When the chemical supply stops, the local community collapses rapidly. Mobile scavengers quickly consume the remaining dying organisms. The sessile creatures perish as their symbiotic bacteria starve. However, new hydrothermal vents open nearby along the ridge axis. Pioneer species must colonize these newly formed mineral chimneys. Larval dispersal represents a critical survival strategy for vent fauna. Ocean currents transport microscopic larvae along the deep rift valley. Researchers deploy sediment traps to measure this larval flux. The larvae drift in a state of suspended metabolic animation. They must locate an active vent before their lipid reserves deplete. Chemical cues in the water column trigger their final settlement. The exact nature of these chemical attractants remains poorly understood. The Pelagia vent field offers another unique biological study site. It lies further north along the central Indian Ridge. Scientists discovered dense beds of Bathymodialus maricindicus mussels here. These deep-sea mussels secure themselves to the basalt using byssal threads. They possess dual symbiosis within their enlarged gill tissues. They host both sulfide oxidizing and methane oxidizing bacterial strains. This dual capacity allows them to exploit fluctuating fluid chemistries. If hydrogen sulfide levels drop, they rely on methane oxidation. This metabolic flexibility ensures their survival in variable environments. Polychaete worms construct delicate tubes among the mussel beds. Branchipolyno cimatillida lives as a commensal resident inside the mussels. This scale worm shares the food particles collected by its host. Alvanellid worms inhabit the hottest outer walls of the chimneys. They tolerate temperatures exceeding 50 degrees Celsius on their tubes. Their bodies produce special proteins to prevent thermal cellular damage. A thick layer of episymbiotic bacteria covers their dorsal surface. These bacteria may provide thermal insulation for the vulnerable worms. The central Indian Ridge separates the African and Indo-Australian plates. This tectonic boundary influences the genetic flow of deep-sea populations. The triple junction to the south creates a dispersal barrier. Species distribution mapping reveals distinct provinces of vent fauna. The Indian Ocean province exhibits a unique evolutionary history. It retains ancient lineages that went extinct in other oceans. Neolepus barnacles attach to the peripheral rocks at the Kyray field. These stalked barnacles represent a very primitive crustacean form. They filter feed using specialized cirri extended into the current. Their presence supports the theory of vent communities as refugia. The deep ocean protects them from major global extinction events. Surface climate changes barely impact these isolated hydrothermal ecosystems. The solitaire vent field features diffuse flow through fractured basalt. Temperature measurements here rarely exceed 60 degrees Celsius. This cooler environment supports extensive fields of stalked suspension feeders. Crinoids anchor themselves to the elevated volcanic ridges. They capture descending particulate matter from the upper ocean layers. This creates a rare intersection of photosynthetic and chemosynthetic food webs. The biological diversity of the central Indian Ridge remains undersampled. Every new ROV dive yields previously unknown invertebrate species. Taxonomists continually describe new genera of copepods and nematodes. These microscopic organisms inhabit the interstitial spaces of the mineral deposits. They graze on the ubiquitous bacterial biofilms covering every surface. The energy flow moves efficiently from bacteria to myofauna. Larger macrofauna then consume these tiny interstitial grazers. heavy metals constantly precipitate from the venting hydrothermal fluids. Copper, zinc, and lead accumulate in the surrounding sediments. Vent organisms have evolved specific mechanisms to handle this toxicity. Metallothionein proteins bind to heavy metals within their cellular tissues. This process sequesters the toxic elements into harmless internal granules. The scalyfoot snail excretes excess sulfur through its iron scales. This detoxification strategy simultaneously provides robust physical protection. Their iron armor deters attacks from predatory crabs and fish. The Dodo vent field sits at 28 degrees south latitude. Japanese researchers discovered this site using the AUV Urashima. Autonomous vehicles map the chemical plumes before visual confirmation. The Dodo field exhibits a highly localized endemic population structure. Genetic drift causes minor variations between these isolated vent fields. Over millions of years, these variations lead to new species. The Okinawa vent field presents an extinct hydrothermal environment. It sits several kilometers away from the active rift axis. The mineral chimneys here have ceased all fluid emissions. The specialized chemosynthetic community has completely vanished from this site. Only the skeletal remains of mussels and clams persist. Deep-sea corals now colonize these towering inactive sulfide structures. Sponges filter the surrounding seawater from these elevated mineral platforms. This succession demonstrates the life cycle of a hydrothermal ecosystem. Active chemosynthesis eventually gives way to traditional benthic suspension feeding. The transition takes thousands of years to fully complete. The geological age of the central Indian Ridge influences biology. It is an intermediate spreading ridge system in tectonic terms. Magma chambers lie deeper here than at the East Pacific Rise. This depth affects the chemical composition of the expelled fluids. Iron concentrations are significantly higher in these specific emissions. The high iron content directly enables the scalyfoot snail's armor. Such biological adaptations are perfectly tuned to local geological conditions. The Tiancheng vent field was discovered by Chinese researchers. Scientific exploration of the central Indian Ridge began decades ago. Early expeditions relied on rudimentary single-beam echo sounders. Researchers mapped broad topographic features during the 1980s. The true complexity remained hidden beneath thousands of meters. In 1993, the research vessel Melville surveyed the region. Scientists deployed towed side-scan sonar arrays behind the ship. These instruments revealed massive fault lines across the crust. Dr. Robert Fisher analyzed the initial bathymetric sonar data. He identified a major tectonic boundary near 25 degrees south. The sonar maps showed a highly fractured basaltic terrain. Water depth averaged 3,200 meters in this southern sector. Deep temperature anomalies suggested active hydrothermal venting nearby. Traditional sampling methods proved inadequate for pinpointing vent locations. Marine engineers needed much more precise underwater navigation systems. In 1997, the Japanese research vessel Kairei launched an expedition. Dr. Kensaku Tamaki led the international scientific research team. They dragged a CTD rosette through the dark water column. The sensors detected significant spikes in dissolved methane gas. Optical backscatter instruments registered dense suspended particle clouds. These readings indicated a massive hydrothermal plume below. The plume hovered 200 meters above the rocky seafloor. Deep ocean currents carry the distinct chemical signature westward. Researchers tracked the signal to 25 degrees 19 minutes south. They recorded the longitude at 70 degrees 02 minutes east. In 2000, the team returned with the Shinkai 6500. This manned submersible could withstand immense hydrostatic pressure. Dr. Ken Takai piloted the craft down to 2,420 meters. External thermometers registered ambient water at 2.4 degrees Celsius. The submersible lights illuminated towering black sulfide chimneys. Scientists named this site the Kairai Hydrothermal Field. Another major discovery occurred during the 2001 research season. The American research vessel NOR arrived at the ridge. Dr. Cindy Lee Van Dover coordinated the biological sampling. The team utilized the remotely operated vehicle Jason. Jason descended to a maximum depth of 3,290 meters. The exact coordinates were 23 degrees 52 minutes south. The recorded longitude was 69 degrees 35 minutes east. Operators in the control room observed the live camera feeds. They discovered a massive new cluster of active vents. Scientists named this location the Edmond Hydrothermal Field. Jason inserted a titanium temperature probe into a chimney. The digital readout displayed an incredible 360 degrees Celsius. High-definition cameras captured detailed images of the mineral deposits. The ROV collected rock samples using robotic manipulator arms. Engineers equipped Jason with a specialized vacuum suction sampler. This device carefully extracted delicate biological specimens from rocks. The tether transmitted gigabytes of scientific data to the surface. Technological breakthroughs revolutionized ridge exploration in the following years. Autonomous underwater vehicles completely transformed deep seafloor mapping. The German Research Institute GMR developed the AUV Abyss. This torpedo-shaped robot operates entirely without a physical tether. It relies on pre-programmed acoustic navigation algorithms for movement. Abyss flies exactly 50 meters above the rugged terrain. It carries a highly sensitive high-frequency multi-beam echo sounder. The sonar pulses generate maps with 1 meter spatial resolution. Traditional ship-based sonar only achieves 50-meter resolution at best. Researchers can identify individual chimney structures on these precise maps. In 2007, the research vessel Sun deployed the AUV Abyss. Dr. Colin Devey directed the Index Marine Exploration Project. The autonomous vehicle surveyed 150 square kilometers of crust. It recorded precise magnetic field variations along the ridge. These magnetic anomalies help calculate long-term tectonic spreading rates. Lithium-ion batteries power the AUV for 22 continuous hours. Short expeditions provide only brief glimpses of ridge dynamics. Scientists require continuous data to understand geological processes. Long-term monitoring programs address this critical oceanographic knowledge gap. Oceanographers deploy complex mooring arrays along the Rift Valley. A typical mooring consists of a heavy steel anchor. A Kevlar line stretches upward toward the ocean's surface. Glass flotation spheres keep the mooring line perfectly vertical. Technicians attach various scientific sensors at specific depth intervals. Current meters record the velocity of deep ocean currents. Acoustic Doppler profilers measure water movement across different layers. Sediment traps collect falling mineral particles over 12 months. Microtemperature loggers monitor subtle thermal fluctuations near active vents. A built-in acoustic release mechanism secures the heavy anchor. Scientists transmit a specific sound frequency to retrieve the equipment. The release mechanism detaches the anchor weight from the line. The glass spheres carry the valuable instruments back up. Seismic activity along the ridge requires constant daily surveillance. Earthquakes indicate magma movement beneath the oceanic crust. Conventional land-based seismometers cannot detect small deep-sea tremors. Researchers established a hydroacoustic monitoring network in the region. They anchored autonomous underwater hydrophones directly to the seafloor. These underwater microphones record extremely low-frequency acoustic sound waves. Sound travels efficiently through the deep oceanic sound channel. The hydrophones capture the acoustic signatures of tectonic microearthquakes. Dr. Maya Tolstoy analyzed extensive hydroacoustic data from the ridge. Her research team identified massive swarms of seismic events. These swarms often precede volcanic eruptions on the seafloor. The scientific instruments sample audio at exactly 250 Hz. High-capacity flash memory drives store the continuous acoustic recordings. Lithium battery packs sustain the hydrophones for 2 entire years. Scientists must physically recover the devices to access the data. Chemical mapping of the water column is highly systematic. Dr. Edward Baker pioneered optical backscatter techniques in this region. His sophisticated instruments measure the turbidity of deep ocean water. Hydrothermal vents release millions of microscopic iron sulfide particles. These suspended particles scatter the light emitted by the sensor. The intensity of scattered light indicates the plume concentration. During a 2009 expedition, technicians performed extensive tow transects. The ship towed the sensor package in a sawtooth pattern. A mechanical winch continuously raised and lowered the steel cable. This method creates a two-dimensional cross-section of the chemical plume. The collected data revealed multiple overlapping chemical water layers. Some mapped plumes originated from completely undiscovered vent fields. Nephelometers measured the exact density of the suspended minerals. Spectrometers analyzed the trace metal composition in real time. This detailed chemical mapping guides future manned submersible dives. International collaboration greatly accelerated the pace of ridge exploration. The Chinese research vessel Dayang Yihao conducted extensive surveys here. The scientific team focused heavily on the southern ridge segments. They deployed the Qianlong autonomous underwater vehicle for mapping. Qianlong navigates the complex topography using forward-looking obstacle avoidance. Its onboard chemical sensors easily detect dissolved hydrogen sulfide. A miniature mass spectrometer measures dissolved deep-sea gas concentrations. The robotic vehicle mapped a large inactive massive sulfide deposit. Inactive deposits lack the distinct thermal signature of active vents. They are extremely difficult to locate using traditional oceanographic methods. High-resolution magnetic sensors identified the oxidized mineral structures instead. The expedition collected massive sulfide ores for thorough geological analysis. These rocky samples contain high concentrations of copper and zinc. Radiometric dating accurately determines the age of the mineral formations. Some massive deposits formed over 50,000 years ago. Biological research missions require highly specialized engineering equipment. Deep-sea organisms perish quickly during standard surface recovery procedures. Extreme pressure changes and temperature shocks cause severe cellular damage. Engineers designed hyperbaric recovery chambers for delicate biological sampling. The ROV places biological specimens inside a thick titanium cylinder. A mechanical seal locks the extreme ambient pressure safely inside. The chamber maintains 300 atmospheres of pressure during ascent. A thermodynamic cooling system keeps the internal temperature at 3 degrees. Microbiologists study these organisms in pressurized chipboard biological laboratories. Dr. Takai cultivated extreme thermophiles from Kai-ray chimney fragments. He utilized a continuous flow high-pressure bioreactor for his experiments. This machine simulates the exact physical conditions of a hydrothermal vent. Long-term benthic observatories provide continuous biological data for researchers. High-definition cameras record the behavioral patterns of endemic vent fauna. Time-lapse photography captures the slow growth rates of deep-sea mussels. Data transmission from the deep ocean remains a significant challenge. Standard radio waves cannot penetrate highly conductive seawater. Scientists rely heavily on acoustic telemetry for wireless communication. Acoustic modems translate digital data into underwater sound pulses. A floating surface buoy receives these complex underwater acoustic signals. The buoy then transmits the information via global satellite networks. The bandwidth of deep-sea acoustic telemetry is extremely limited. It can only transfer a few kilobits of data per second. This slow speed is sufficient for simple temperature and pressure readings. High-definition video still requires a physical fiber optic cable connection. Some monitoring stations utilize expendable autonomous data capsules instead. The station writes data to a small buoyant fiberglass pod. The pod detaches automatically and floats rapidly to the surface. An Iridium satellite antenna broadcasts the stored data to laboratories. This backup system ensures data survival if the main instrument fails. In 2013, researchers explored the northern segments of the ridge. They utilized the highly advanced German ROV Kiel 6000. This robotic vehicle is officially rated for depths of 6,000 meters. The scientific expedition investigated the remote Pelagia hydrothermal field. The exact coordinates are 16 degrees 14 minutes south. The recorded longitude is 66 degrees 53 minutes east. Kiel 6000 features dual titanium manipulators with force feedback. The remote pilot can physically feel the resistance of the rocks. A high-definition macro camera filmed microscopic mineral formations up close. The ROV deployed a specialized isobaric fluid sampler device. This titanium syringe extracts pristine hydrothermal fluids from the vent. It completely prevents chemical contamination from the surrounding cold seawater. The trapped fluid contains dissolved heavy metals and volatile gases. Isotope analysis traces the geological origin of the hydrothermal water. The chemical signature differs significantly from the Kai-ray field. Future scientific expeditions will rely on persistent autonomous platforms. Ocean gliders are becoming standard tools for continuous ridge observation. A glider controls its physical buoyancy by pumping internal oil. The central Indian Ridge offers unique geological insights. It spreads at a moderate 40 mm per year. This classifies it as an intermediate spreading center. The Mid-Atlantic Ridge separates much slower by comparison. The Atlantic plates move about 25 mm annually. Conversely, The East Pacific rise expands very rapidly. The Pacific plates diverge at over 100 mm yearly. These varying speeds create distinct topographic profiles underwater. Slow ridges typically form very deep central rift valleys. Fast ridges build broad and elevated volcanic tectonic domes. The central Indian Ridge exhibits a transitional architecture. It features both shallow rifts and steep axial volcanoes. Hydrothermal venting styles also change with local spreading rates. Pacific vents typically produce brief and highly active smokers. Atlantic systems generate long-lasting and massive sulfide deposits. Indian Ocean vents seamlessly blend these two thermal behaviors. The Chi-ray field shows Pacific-style rapid fluid expulsion. The Edmund field builds massive Atlantic-style mineral chimneys. Geochemist Christopher German studied these global vent distributions extensively. His research highlighted the Indian Ocean as a biological bridge. Fauna here share genetic traits with both adjacent oceans. The ridge acts as a massive evolutionary underwater crossroads. Tectonic forces directly shape the migration routes of abyssal life. Deep ocean currents transport microscopic larvae across these rocky divides. Comparing these global ridges reveals fundamental planetary cooling mechanisms. Earth constantly releases internal heat through these fractured oceanic seams. Each distinct ocean basin tells a different part of the story. The Indian Ocean provides the crucial missing intermediate data points. The global mid-ocean ridge system stretches for 65,000 kilometers. It forms the longest continuous mountain range on our entire planet. The central Indian Ridge connects the Atlantic and Pacific tectonic networks. This vital connection allows marine biologists to track species migration patterns. Deep ocean currents flow slowly through these jagged underwater mountain passes. These currents carry essential nutrients to highly isolated biological communities. This intermediate environment holds vital clues to early Earth. Scientists study these deep vents to understand chemical abiogenesis. Life likely started in very similar deep-sea extreme conditions. The Chi-ray field produces unusually high dissolved hydrogen concentrations. Ultramafic mantle rocks interact directly with heated seawater here. This specific chemical reaction is scientifically known as serpentinization. Serpentinization naturally generates hydrogen gas and highly alkaline fluids. Early Earth oceans were naturally highly acidic and iron-rich. Alkaline vent fluids mixing with acidic seawater creates electrical energy. This natural chemical gradient mimics the function of a biological cell. Geologist Michael Russell proposed this alkaline hydrothermal vent hypothesis. He suggested natural mineral pores acted as primitive cellular membranes. Iron-sulfur minerals within chimneys catalyzed the earliest organic reactions. Carbon dioxide and hydrogen combined to form simple organic molecules. Biologist William Martin expanded upon this metabolic origin theory. They theorized that life began without any sunlight or photosynthesis. The central Indian Ridge provides a perfect modern testing laboratory. Its unique rock composition closely mirrors the ancient Hadean crust. Researchers collect sterile fluid samples from 3,000 meters deep. They analyze the isotopic signatures of dissolved deep-sea carbon compounds. Abiotic methane forms naturally within these cooling volcanic basalt rocks. Specialized microbes use this abiotic methane as a primary food source. This represents a completely independent biological energy production cycle. Complex RNA molecules might have assembled in these thermal gradients. Thermophoresis concentrates organic molecules inside tiny porous mineral structures. Complex chemical polymers could form under these extreme pressure conditions. The deep ocean effectively shields these reactions from surface radiation. Early Earth faced constant ultraviolet bombardment and frequent asteroid strikes. The abyssal ocean ridges offered a highly stable, warm sanctuary. Studying the central Indian Ridge helps modern astrobiologists today. Similar hydrothermal systems likely exist on distant icy planetary moons. Jupiter's moon Europa probably hides active underwater volcanic vent systems. Saturn's moon Enceladus ejects massive plumes containing silica nanoparticles. These particles indicate ongoing high-temperature rock and water interactions. The Indian Ocean vents serve as accessible extraterrestrial research analogues. The study of extremophiles here has revolutionized modern biological sciences. Archaea microbes thrive in temperatures exceeding 100 degrees Celsius. Their unique cellular enzymes remain highly stable under immense thermal stress. Pharmaceutical companies study these specific enzymes for new medical drug development. The polymerase chain reaction relies on similar heat-resistant bacterial proteins. This specific technology makes modern genetic DNA testing physically possible today. Deep-sea genetics could unlock completely new treatments for severe human diseases. Exploring these deep extraterrestrial analogues requires immense modern engineering effort. The physical underwater environment actively destroys fragile human technology. Ambient water pressure at 3,000 meters is absolutely crushing. It exceeds 300 atmospheres of constant absolute physical force. Every square inch of equipment bears thousands of heavy pounds. Submersibles require perfectly spherical titanium pressure hulls for human safety. Even microscopic flaws in the metal cause instant catastrophic implosions. The remotely operated vehicle Jason operates safely in these extremes. It utilizes specialized syntactic foam for deep water neutral buoyancy. This foam consists of millions of microscopic hollow glass spheres. It resists extreme compression while providing essential upward physical lift. Superheated hydrothermal fluids present another severe mechanical engineering challenge. Vent water exits the fractured crust at nearly 400 degrees. This dark fluid is highly acidic and extremely chemically corrosive. It rapidly dissolves exposed delicate electronics and unprotected metal joints. Robotic manipulators use strong titanium and specialized synthetic industrial plastics. Sharp temperature gradients cause severe thermal shock to sensitive instruments. Standard camera lenses crack when moving from cold to boiling water. Thick sapphire glass effectively protects the delicate external optical sensors. Data communication is another major hurdle in deep ocean research. Standard radio waves cannot penetrate the dense global saltwater column. Acoustic modems transmit essential data using low-frequency underwater sound waves. This acoustic method is incredibly slow and highly prone to interference. Research robots rely on miles of reinforced fiber optic tether cables. These heavy cables transmit high-definition video to the surface ship. Managing a 3-mile cable in strong deep currents is difficult. The research vessel must maintain incredibly precise dynamic spatial positioning. Advanced satellite coordinates keep the massive ship locked over the site. Computer-controlled thrusters counteract unpredictable surface winds and large ocean swells. A snap tether means losing a multi-million-dollar scientific robot. Marine engineers constantly monitor cable tension and complex vehicle telemetry. Battery technology also strictly limits autonomous underwater vehicle daily operations. Lithium-ion spheres power the mapping drones for very limited hours. Recharging requires bringing the heavy vehicles back to the ocean surface. Every single dive involves hours of slow descent and ascent time. Bottom time for actual scientific observation always remains incredibly precious. Oceanographic research vessels cost tens of thousands of dollars daily to operate. Weather conditions frequently force the sudden cancellation of planned robotic dives. High surface waves make deploying the heavy submersible vehicles incredibly dangerous. The massive lifting cranes must counteract the unpredictable rolling ship movements. Specialized winch operators require years of intense training and practical experience. Despite these massive challenges, commercial interest in the ridge grows. Hydrothermal vents create massive seafloor polymetallic massive sulfide deposits. These deposits contain highly concentrated and valuable industrial heavy metals. Pure copper, zinc, and gold precipitate directly from the cooling fluids. The Edmund vent field hosts particularly large underwater mineral mounds. These towering structures have accumulated slowly over many thousands of years. Some older inactive chimneys contain highly sought rare earth elements. Neodymium and yttrium are absolutely crucial for modern consumer electronics. Green energy technologies require massive amounts of these specific metals. Wind turbines and electric vehicle batteries drive intense global market demand. Terrestrial land mines face declining ore grades and strict environmental protests. The deep ocean represents a vast and untapped raw mineral frontier. Mining companies design massive robotic seafloor trenchers and heavy cutters. These industrial machines would grind the sulfide chimneys into fine gravel. A powerful slurry pump would transport the heavy ore to surface ships. The central Indian Ridge falls entirely under complex international legal jurisdiction. No single sovereign country owns this remote section of the seafloor. The International Seabed Authority legally manages these shared global resources. They issue strict exploration contracts to various interested national organizations. China and South Korea currently hold specific mineral exploration licenses here. Government contractors map the rugged terrain and sample the mineral content. They carefully assess the economic viability of future deep extraction operations. Current geological estimates suggest millions of tons of easily recoverable copper. However, the physical extraction process poses severe and lasting ecological risks. Deep mining would instantly destroy ancient and fragile biological vent communities. Geologists use advanced sonar mapping to locate hidden buried sulfide deposits. Autonomous drones fly just meters above the jagged volcanic ocean floor. They detect incredibly faint magnetic anomalies within the solid basalt crust. These magnetic signatures often indicate massive buried metallic ore bodies below. Core sampling drills extract solid rock cylinders from the deep seabed. Laboratory analysis reveals the exact chemical percentage of valuable trace metals. Marine biologists strongly advocate for strict deep-sea environmental conservation measures. Active hydrothermal vents are officially classified as vulnerable marine ecosystems. Rare species like the scalyfoot snail exist absolutely nowhere else. This unique snail relies on iron sulfides to build its metallic shell. The International Union for Conservation of Nature lists it as globally endangered. It is the very first species threatened primarily by deep-sea mining. Ocean scientists worry about the widespread ecological impact of sediment plumes. Heavy mining machines would stir up massive dark clouds of fine dust. Strong deep ocean currents could carry this toxic dust for many miles. The suspended mineral particles would quickly smother delicate filter-feeding organisms. Fragile glass sponges and deep-water corals cannot clear the heavy sediment. The central Indian Ridge constantly shapes our global climate system. Immense heat radiates from the fractured tectonic plate boundaries. Hydrothermal vents act as powerful thermal engines for the ocean. This geothermal energy warms the surrounding deep abyssal waters. Bottom water temperatures rise by tiny but highly significant margins. Sensors detect persistent thermal anomalies of 0.05 degrees. This slight warming helps drive global thermohaline ocean circulation patterns. Warm deep water masses slowly rise and move across basins. These abyssal waters circulate around the entire globe over many centuries. The slow movement of cold water regulates temperatures on the continents. Deep ocean currents act as a massive planetary air conditioning system. The central Indian Ridge is a vital component of this global machine. Without this geothermal heat, the deep ocean would become completely stagnant. Oxygen levels in the deep sea would drop to dangerously low levels. The thermal vents provide the necessary energy to keep the water moving. Deep ocean currents transport this thermal energy across vast distances. The oceanic ridge acts as a hidden pulse within the sea. Heat flux measurements show continuous energy transfer into the water. Thousands of gigawatts of power dissipate along the fault lines. This continuous energy release prevents total deep ocean water stagnation. Deep water mixing sustains complex global weather patterns above the surface. The Indian Ocean relies heavily on this hidden thermal input. Dr. Alan Hastings models these deep ocean heat transfer mechanisms. His research team measures thermal gradients near the Edmund Vent Field. They deploy highly sensitive probes into the active chimney structures. The gathered data reveals a complex interaction between crust and ocean. This thermal exchange regulates large-scale planetary climate cycles over time. The ridge also plays a crucial role in global carbon sequestration. Chemical reactions within the basaltic crust trap dissolved carbon molecules. Seawater constantly circulates through the porous volcanic rock layers below. Dissolved inorganic carbon reacts with magnesium and calcium silicate minerals. This process forms solid carbonate minerals deep within the seabed. Millions of tons of carbon are permanently locked away here. The sheer volume of basaltic rock offers nearly limitless carbon storage potential. This natural process has regulated the Earth's climate for billions of years. Scientists are studying how to potentially accelerate this natural carbon mineralization process. Understanding these deep-sea mechanisms could help mitigate modern climate change impacts. The ocean floor acts as a silent guardian of our atmospheric balance. Chemosynthetic bacteria also contribute to this massive oceanic carbon sink. Microbes consume carbon dioxide to build their complex cellular structures. Massive microbial mats cover the cooling underwater lava formations completely. When these organisms die, their organic matter settles into deep sediments. This biological pump removes carbon from the active global atmospheric cycle. The oceanic crust functions as a massive, permanent planetary sponge. Weathering of fresh basalt absorbs significant greenhouse gases over millennia. Dr. Sarah Jenkins studies these mineralogical deep ocean carbon traps. Her research quantifies the carbon storage capacity of oceanic ridges. The central Indian Ridge holds vast amounts of stabilized carbon compounds. This unseen mechanism helps balance the atmospheric composition far above. Protecting these geological processes ensures long-term climate stability for Earth. Human understanding of these deep carbon cycles remains quite limited today. Scientists continue to formulate new questions about this massive ridge. Vast stretches of the central Indian Ridge remain completely unexplored. Only a tiny fraction of the hydrothermal vents are currently mapped. Future research will focus on locating hidden active geothermal fields. The upcoming 2026 Indian Ocean Ridge Initiative plans extensive surveys. Autonomous underwater vehicles will map the terrain at millimeter resolution. These robotic explorers can operate independently for several consecutive months. They will use advanced synthetic aperture sonar to scan the seafloor. High-resolution bathymetry will reveal completely undiscovered geological formations. Dr. Hiroshi Tanaka leads the engineering team for these deep drones. His vehicles can withstand immense pressures at 4,000 meters deep. The robots will sample water chemistry along the entire ridge axis. Chemical sensors will detect faint traces of dissolved hydrogen sulfide. These chemical plumes often indicate nearby undiscovered hydrothermal vent systems. Researchers hope to find entirely new classes of extremophile organisms. Genomic sequencing of deep-sea bacteria offers immense modern scientific potential. Unlocking their unique genetic code could revolutionize modern medical biotechnology. Enzymes from heat-resistant microbes have numerous potential pharmaceutical applications. Marine biologists will catalog thousands of previously unknown benthic invertebrate species. Advanced submersible designs will allow humans to stay at depth much longer. The biological diversity of this deep region remains a profound mystery. New technologies will transform our understanding of tectonic plate movements. Seismologists plan to deploy long-term benthic observatories along the fault line. These specialized sensor arrays will monitor microearthquakes in real time. Acoustic modems will transmit seismic data directly to ocean surface buoys. Satellites will then relay this critical information to laboratories worldwide. New fiber optic cables will connect these deep observatories to the mainland. This will allow for the continuous streaming of high-definition deep-sea video. Students around the world will watch deep ocean ecosystems in real time. The democratization of deep-sea data will inspire the next generation of scientists. Scientists will carefully track magma movements beneath the solid oceanic crust. They can measure tectonic drift rates with truly incredible precision. The tectonic plates separate at roughly 2.4 centimeters annually. Highly sensitive strain meters will record the subtle deformation of the seafloor. Dr. Elena Rostova designs these resilient deep ocean monitoring stations. Thick titanium housings protect the delicate instruments from corrosive saltwater. Advanced solid-state batteries provide reliable power for up to 10 years. These observatories will capture the exact birth of new oceanic crust. Researchers will witness powerful geological processes as they actually happen. Machine learning algorithms will analyze the massive datasets generated by sensors. Artificial intelligence can identify subtle patterns in deep acoustic emissions. This predictive technology may eventually forecast underwater volcanic eruptions accurately. The central Indian Ridge serves as a massive natural geological laboratory. Every scientific expedition yields unexpected data that challenges existing theories. The spectacular wonders of the deep ocean demand our careful protection. Hydrothermal vent ecosystems are incredibly fragile and highly localized environments. These unique biological communities rely on precise chemical balances to survive. Slight environmental changes can cause entire vent colonies to collapse completely. The delicate balance of life here took millions of years to evolve. Once destroyed, these hydrothermal vent communities may never fully recover or return. The loss of genetic diversity would be a tragedy for future scientific discoveries. Global cooperation is essential to establish enforceable deep-sea conservation treaties immediately. We must act as responsible stewards for these hidden underwater ecosystems today. The looming threat of deep-sea mining shadows these pristine habitats. Mining companies seek valuable minerals deposited by the hot hydrothermal fluids. Massive sulfide deposits contain rich concentrations of valuable copper and gold. Extracting these geological resources would destroy the delicate mineral chimney structures. Heavy industrial machinery would crush the rare biological communities living there. Thick sediment plumes from mining operations could smother adjacent vent fields. The International Seabed Authority currently regulates these remote international ocean territories. Dedicated conservationists advocate for strict protections around active hydrothermal vents. Establishing permanent marine protected areas is vital for preserving deep biodiversity. Dr. Michael Vance campaigns tirelessly for the preservation of these ridges. His ecological models demonstrate the severe impacts of physical seafloor disturbance. We must carefully balance global resource demands with strict ecological preservation. The intrinsic value of untouched ocean wilderness cannot be easily quantified. These deep-sea environments represent our beautiful planet in its rawest form. Protecting the central Indian Ridge ensures the survival of ancient biological lineages. Deep-sea exploration reveals the profound interconnectedness of all Earth systems. The dark ocean floor is not a barren or lifeless wasteland. It is a dynamic realm of continuous geological creation and destruction. Superheated boiling fluids meet freezing waters to forge new mineral structures. Relentless tectonic forces slowly reshape the fundamental geometry of our planet. Unique life thrives in the most extreme physical conditions imaginable here. The incredible resilience of these deep-sea organisms inspires constant scientific wonder. We are just beginning to properly understand this vast alien world. Every single dive into the abyss expands our collective human knowledge. The central Indian Ridge remains a powerful testament to geological power. Its silent underwater mountains stand as permanent monuments to deep planetary time. The scientific mysteries hidden within its deep valleys are nearly infinite. We invite you to deeply appreciate these unseen underwater landscapes tonight. Imagine the towering mineral chimneys venting dark chemical smoke into the water. Visualize the pale crabs moving slowly across the jagged black basalt. Picture the transparent shrimp feeding near the boiling underwater thermal springs. This hidden ecosystem operates entirely without the warming light of the sun. It is a complex world sustained purely by the Earth itself. The scientific journey along the central Indian Ridge concludes peacefully here. Our detailed exploration of this submerged mountain range is now complete. The robotic submersible vehicles return safely to the distant surface above. The deep ocean environment returns to its natural and undisturbed state. The immense heavy pressure of the water maintains a profound silence. The flat abyssal plains stretch out endlessly into the dark distance. Hydrothermal vents continue their ancient and steady chemical exhalations without pause. Massive tectonic plates drift apart by microscopic fractions of a single millimeter. The Earth breathes slowly through these deep and hidden volcanic fissures. The gentle natural rhythm of the ocean provides a calming presence. Steady deep ocean currents wash over the rugged basaltic mountain peaks.